Hello and welcome to another instructional video, another episode in this course as we continue to look at chemistry and specifically we're going to be looking at in this video and in several of the videos to come, we're going to be looking at reactions. One of the really cool things about chemistry is we get to understand the chemical reactions that are happening all over around us every day, all the time. We've been spending a lot of time previous to this video, talking about the particles that make up chemistry, that make up matter. The particles, even the subatomic particles, the protons, the neutrons, the electrons. We've been talking about compounds and molecules, and what they look like, and how they may be arranged. And now we're going to be looking at, well, what about when one compound is pulled apart, the bonds are broken, everything is rearranged, and new compounds are formed that would come up, and that would be called a chemical reaction. How does that happen? What does that look like? Are there patterns that we can recognize, different types of reactions? So this video is going to be focusing on exactly that, types of chemical reactions. Are there predictable patterns that we can observe, recognize, and predict in order to better understand what's happening at the molecular level when chemical reactions occur? All right, let's look at our models. These are powerful models as we dive into these types of reactions. So model 1 is entitled Types of Reactions, and you've got set A, set B, set C, and set D. Obviously it looks kind of like we're going to be trying to distinguish how all of these reactions are similar in set A, how all of these are similar in set B, and same with set C and set D. So let's look at some of the questions here. Number 1, the chemical equations in Model 1 contain the phase notations. Phase means what state are they in. S, L, G, and AQ. Match each symbol with its meaning. So if it is a liquid, you will often see in parentheses the letter L behind that compound. If it is a solid, you will see S. If it is a gas, you will see G. So those are the three very common phases that you may be familiar with. If the solid is dissolved in water, then you're going to see AQ. AQ stands for aqueous. So any solid that is dissolved in water, it dissolves, and often what the case might be also that it breaks apart into ions, as you'll see in some of these reactions. We are going to put an AQ behind that to tell us that it is in solution, a water solution. Based on the examples provided, which set or sets of reactions in Model 1 typically involve ions in solution? In other words, ions in solution means we're looking for AQ. Would that be A, B, C, or D? Well, let's just scan quickly up here, see what we have. And we notice that in set A, there are gases and solids involved, all gases. Here's a little AQ, AQ, AQ happening. In set B, we have solids, we have gases, liquids, solids, gases, liquids. Doesn't look like there's any AQ there. Here in set C, AQ right there. You've got AQ, AQ in this one, AQ in this one. Every single one of these have AQ, aqueous solutions. And set D as well, every single one of those is aqueous solutions. So the most prominent two sets of reactions that have AQ in them would be C and D. Okay. Based on the examples provided, which set or sets of reactions in Model 1 typically involve gases and or solids? So gases and solids we're looking at, as we already talked about. It's not that we never see aqueous. Here obviously in set A there are some aqueous solutions, but predominantly set A has gases, liquids, and solids. Same with set B, gases, liquids, and solids here. So gases and or solids, that would be gases, liquids, no, gases and solids. Yeah, I would say you could argue A or B. I think A or B have gases and solids involved for the most part. Okay. C and D, by the way, those are types of reactions that are going to happen most likely in aqueous solutions. That's why they're pointing that out. And we'll talk about what those two types are up here. But those two types are most likely, almost always, going to occur in a water solution. That's why they want to point that out too. Number 4, match each description below to one of the reaction sets, A, B, C, D, C, or D. So they're going to describe what's happening here in words, and we're going to try to see if we can recognize that looking at the different types of reactions. So this is ionic compounds dissolved in water switch partners. Well, let's see if we can find out what's happening up here. I have to have an aqueous solution, so I know it's either C or D. In C, I have lone elements reacting with a compound that is in an aqueous solution, and that lone element, you might notice, after the reaction occurs, is now part of a compound. So, just so you know, on the left side of our reaction, those are called reactants. Then we have an arrow to show that a reaction occurred, meaning the bonds were broken. Those reactants have bonds, they're bonded together. Those bonds are broken. Things are rearranged and new bonds are formed, new compounds are created. And over here we have products. Okay? Reactants are always on the left, products are always on the right. In set D, you'll notice that the reactants are all in aqueous solution, and then a reaction occurs, and we have over on the other side, they are in aqueous solution, or they might be a solid or liquid, but most of these are aqueous solution as well. Let's dive into this one a little bit further, because you'll notice here you've got two compounds in aqueous solution. They come together, there's your plus sign, and after the reaction now, arrow tells us it's a reaction, they have switched partners, meaning now the silver, Ag, is no longer with NO3, it is with the other nonmetal from the other compound, Cl. And the Na is now with the NO3. So they did indeed switch partners, and you have new compounds over here as products. And I'm just going to point out that one of those products formed a solid that is not soluble, it doesn't dissolve in water. The other compound is still dissolved in water. So, to answer the question, that would be D. Ionic compounds dissolved in water, AQ, they switch partners. The metals are going to switch partners and join and make compounds with the other set of nonmetals from the other compound. One compound breaks into elements or smaller compounds. So, this one, on the reactant side, you're looking for just one compound. Well, that should be easy to find. On the reactant side, we're looking for just one compound, and that would be set B. Notice on the right side, sorry, the left side here, all of the reactants are a single compound. So that would be set B. C, two or more elements or compounds combine to form one product. So two or more elements or compounds, these would be your reactants on this side, form just one product. This is your product on that side. So let's see if we can find where there's just one product. And that would be all here. On the right side, you have only one single compound as your product. That is set A. Part of an ionic compound is removed and replaced by a new element. Well, we only have C left. As mentioned earlier, you've got a metal here, in this case zinc, and that zinc, after the reaction occurs by zinc replacing iron. Now it's iron that's left by itself, and zinc is in the compound. So that's what they're describing here, and that is C. Define the following terms as they are commonly used in the English language. Synthesis, you can just think as combining, combination. Okay, things are coming together. Decomposition, you're breaking it apart. And replacement means that you have a switching. So there's going to be a switch. Something is going to take the place of something else, or like a substitution. Number 6, here's a key point. The 4 sets of chemical reactions shown in Model 1 have the following general names. Discuss within your group which name belongs to which set of chemical reactions. Write the name in the appropriate place in Model 1. So let's think about synthesis. Synthesis means they have to come together. It's going to be a combining of particles, compounds, to make a single compound. So synthesis would be set B. Then we have decomposition. Decomposition is something breaking apart. So that would be A. Oops, I am terribly sorry. I'm sorry, I messed this up. Synthesis is over here. My apologies. Synthesis. Okay. 2 things coming together to form just one. All right. Over here we have decomposition. Decomposition means we've got one item breaking apart into 2 or more. All right. Sorry about that. Set A is synthesis. Set B is decomposition. And now we just have the other 2 here. These are in aqueous solutions. These are types of replacement reactions, or substitution reactions, or displacement reactions sometimes they're called. So we have single and double. So if there's just one lone element that is going to replace something, this is your single replacement. And over here you've got 2 metals, both of them switch places. This is a double displacement, or a replacement, whichever term they use here. Okay, they say replacement. I said displacement. Either one I think is acceptable. Single replacement or double replacement. Can 2 elements be used as reactants for a synthesis reaction? If yes, give at least one example to support your answer. Can 2 elements, just elements, for synthesis? So let's look back up here. We're going to find synthesis. That was set A. 2 elements. Indeed, we've got nitrogen. Nitrogen is diatomic, that's why it's N2. Combining with hydrogen. Hydrogen is also diatomic to form NH3. And in this case, yes, 2 elements can indeed be a part of a synthesis reaction. And I just showed you the reaction that supports that. Can 2 compounds be used as reactants for a synthesis? Yes, that is true. We got 2 compounds. Here is magnesium oxide. Here is dihydrogen oxide, also known as water. Dihydrogen monoxide, actually. And you have 2 compounds forming a product, a single product over here. And I gave you an example there. What types of substances, elements or compounds, are seen in the products of decomposition reactions? So are we going to see elements or compounds as products in decomposition? Well, decomposition is set B. That's where you have a single item broken apart. You are going to see compounds, as is the case here. You also are going to see elements, as is the case in the 2nd and 3rd reaction. So you're going to see both. In single replacement reactions, do any of the atoms change their charge? We're going to talk about that in a second. If yes, use an example from Model 1 to describe the changes that take place. So let's look at single replacement, that's set C. Are they changing their charge? Here's what I mean by that. Let me just take one of these. Let's take this iron chloride. I'm going to write it down here for us to look at. This looks like iron 3 chloride combining with zinc. The reaction then, zinc is going to come in here and take iron's place. And we get, we get then the iron is by itself, and the zinc is going to form zinc chloride. Okay, now let's just point a few things out here. Over here by itself, zinc Zn, the symbol is zinc, or Zn is for zinc, it has no charge on it. It's not an ion. There's no superscript plus or minus number here. This is neutral. So the charge here is 0. Over here, this is an ionic compound, FeCl3. What that means is you've got, Fe, which has a charge of 3 plus ion, combining with 3 chloride ions. Remember, they combine in a ratio such that the compound is neutral. So in this case, as a compound, Fe came into this compound because it was an ion attracted to the 3 ions of chloride, the chloride ions. Now, after the reaction, look what Fe is. Fe is a lone element, all by itself, no charge up here. There's no charge as a superscript. So its charge is 0. But now the zinc is in the ionic compound. How does that happen? Well, zinc forms a 2 plus ion, and it is combining with 2 chloride ions. It only needs to combine with 2 because it has a 2 plus charge, so to make a neutral compound, you only need 2 chlorides. You don't need 3, as is the case over here with the iron 3. So now zinc has a charge on it. It went from 0 to now being an ion and bonding with the chloride. So do they change their charge? Yes. So iron went from a plus 3 ion right here to neutral, and zinc went from neutral 0 to a plus 2 ion in the compound. Okay, that's going to come up later as we talk about redox reactions, reduction and oxidation. That's going to come up in the future, so I'm just giving you a little bit of a heads up there. In double replacement reactions, do any of the atoms change their charge? If yes, use an example from Model 1 to describe. Let's look at double displacement. That is set D. Set D, let's look here. In this case, you've got silver nitrate, and it is going to then, over on the other side, become silver chloride. But the charges are the same on either side for silver. On this side, it is a plus 1, combining with the nitrate, which is a negative 1. And over here, it is combined with the chloride ion, which is a negative 1. Silver is still a plus 1. It's in a 1-to-1 ratio. Same thing with sodium. On this side, it is a plus 1 combined with 1 chloride, which is a negative 1. And on the other side, it is sodium combined with nitrate. Each of those are 1 each because sodium is plus 1, nitrate is a negative 1. So the charges don't change because these are all ions. No change in the charges in this case. You are working with all ions in compounds, so the charges are not going to change. But here, back in number 10, we were working with a solid zinc or solid iron. These are elements. They don't have a charge on them. They're not ions. So there is going to be a change when they go from element, just from the element, to the compound. Choose one example from the set of synthesis reactions in Model 1. Write the chemical reaction in reverse, and I'm going to look ahead here a little bit. Label the reaction written in Part A with one of the reaction types in Model 1. So, in this case, if we write it in reverse, let's take Model 1, synthesis, right? Synthesis, and let's write it in reverse. So let's go ahead and take this lithium sulfide here. Lithium sulfide this is going to then decompose into your lithium and your sulfur. Lithium and sulfur. Okay, and we've got Sulfur, by the way, as an element is S8. That's how it is formed. 8 particles are kind of always forming 1 unit of sulfur. And sulfur is a -2 like oxygen, so lithium is a +1, so you need 2 of those. If we were to balance this, by the way, we'll talk about balancing, I think, in the near future a little bit more, but you always have to have the same number of each element on both sides. So as I write my compounds, here's lithium sulfide, and if that decomposes into lithium and sulfur, I then need to make sure I have the same number of both elements on either side. You can't lose or mysteriously gain atoms. So we go through a process of balancing equations here. For example, if I have 8 sulfurs over here, then I'm going to need 8 on the other side. You don't change the formula though. Don't put a subscript here. That changes the whole formula. I put a number in front, and I'm going to take the whole compound times 8. Well, now I have 2 lithiums in the compound, but I've got 8 compounds. That means I've got a total of 16 lithiums, so I have to have a 16 over on this side. Now I have the same number of each element on both sides. That's balancing equations. Okay? If we put this in reverse, S8 plus 16Li, and we have 8Li2S. This decomposition reaction has now become a synthesis reaction. Okay? That's what they're getting at here. This is now labeled a reaction. This is now a synthesis. Okay? So decomposition and synthesis, they are reverse directions of each other. Identify each of the reactions below as synthesis, decomposition, single replacement, or double replacement. So there's just a few key things that you have to look for. If it is a synthesis, it has only one product. So this would be your synthesis. If it has only one reactant, then it is going to be decomposition. So I'm just going to scan quickly. Here's another one product. That would be synthesis. And looks like that might be, here's one reactant. Looks like that is decomposition. Now, the other ones, single displacement or single replacement and double replacement, I'm looking for single, I'm looking for a compound and a single element. So here we have compound, single element. Here we have compound, single element. So these are all single replacement, single replacement. That leaves the other two for 2 compounds that are going to basically switch partners. 2 compounds, compound, compound. The metals are going to switch partners. So this would be double replacement and double replacement. Here again, the hydrogen, I know it's not a metal, but it acts like one, is going to now combine with the hydroxide. The sodium is going to combine with the sulfate. Alright? A student writes the following incorrect, we got to see what's wrong with it here, incorrect chemical equation for the synthesis of magnesium oxide. So magnesium plus oxygen yields magnesium oxide. What is wrong with that, if anything? And then another student writes the following incorrect. So there are 2 incorrect equations. We have to discover what's wrong with these. Well, here's what you have to be careful of. When you have a chemical reaction, you have to realize that the compounds on the left, the reactants, are not going to be the same as the compounds on the right. New compounds are formed. New bonds are formed. New rearrangements. New arrangements. They're going to be completely rearranged, and new molecules and compounds are formed. So you can't just write it the same way as the reactant side when you're writing your products. Even the ratios don't have to be the same. They might be, but the ratios are going to be completely different possibly too. So you can't depend on the reactants to write your products. So in this case, here I have a reactant of O2, here I have a reactant of just of Mg. These now are going to, you've got an atom of magnesium, you've got 2 bonded together, 2 oxygens bonded together here all right? And they're going to break apart. This bond is going to be broken, so you then have two free oxygens. And those two free oxygens then are going to bond with the magnesium. But remember, oxygen has a charge of 2 negative when it becomes an ion. So I just need one oxygen for every one magnesium, because magnesium has a 2 plus. So they're not going to combine in a 1 to 2 ratio. It's just one of each of them. So what does this poor oxygen do here? Well, it's got to find its own magnesium. So this magnesium atom brings in a friend, and now we form another bond here. So now we have two of them. We've got a magnesium oxide here, and we have another magnesium oxide here. But it's not MgO2. It's not Mg bonded with two different oxygens. That's not what happens. It is Mg bonded with an oxygen, and then if we need another one, we have a separate Mg bonded with another oxygen. Two different compounds, same compound, but two different ones. So this is the wrong formula for magnesium oxide. It should be Mg plus O2. Oxygen is always diatomic. That's the correct formula for elemental oxygen. Produces magnesium oxide, just MgO. If I was to balance this now, I would realize, oh, I see there are two oxygens on the left side. Well, those two oxygens created two different magnesium oxide compounds over here, and therefore I needed two separate magnesium atoms to make this reaction work. That is balanced now. The incorrect part of this problem is that magnesium and oxygen, we forgot, or the student forgot, that oxygen is diatomic. So if it's diatomic, you have to write the correct formula for oxygen, which is O2. They always travel in pairs. Oxygen is always with a buddy. They're in our atmosphere holding hands all the time. So we got magnesium and oxygen creating magnesium oxide, and if we need to balance that, again, same thing. Those two oxygens are going to create two different magnesium oxide compounds by using two magnesium atoms. Okay? Magnesium oxide and O2. So we just said incorrect formula for magnesium oxide, and the second one said forgot that oxygen is diatomic. O2 always. Write the correct balanced chemical equation for the synthesis of magnesium oxide, and we just did that already. Mg plus O2 producing magnesium oxide, and we balance it by putting a 2 here and a 2 there. A student writes the following incorrect chemical equation for a single replacement reaction between lithium bromide and fluorine. This is incorrect. We got to find the mistake somewhere. We'll look at it in a second. In a single replacement reaction, part of an ionic compound is removed and replaced by a new element. What element will fluorine replace in lithium bromide? Well, what's going to happen here is fluorine is going to look to kick something out of the compound over here. Fluorine is a nonmetal. It's going to kick out the other nonmetal. It can't kick out the metal. The metal, this ionic compound has to be a metal. Lithium is your metal. Bromine is your nonmetal. So to keep it as an ionic compound, you can't have a nonmetal and a nonmetal. This metal lithium is going to be attracted to an anion, which is a nonmetal ion. So if it's going to give up bromine or bromine, it's going to then be attracted to the fluorine. Okay? So here's what happens is the fluorine is going to kick out the Br. What is wrong with the student's prediction? Well, he has the fluorine kicking out the metal. That is wrong. Okay? Predict the products and write the correct balanced equation for the single replacement reaction between lithium bromide and fluorine. So, if we do this correctly, we are going to write down our products: lithium bromide. Lithium is a +1, bromide ion is a -1. We're all set. Plus fluorine, which is diatomic, always appears as F2. Reaction occurs, which means bonds are going to be broken. So this molecule right here, LiBr, you have Li atom bonded with a Br. You've got F2, which basically means you have an F fluorine atom bonded with another fluorine atom. These bonds are going to be broken right here and here. Now those atoms are free to move around, rearrange themselves, find new partners, and create new compounds. So what happens? Well, it looks like, according to the reaction up here, lithium is going to be all by itself. So lithium says goodbye. Oh, but this is incorrect. Sorry, this is incorrect. So we need to write the correct one. It is going to be the Br that gets kicked out. This fluorine is going to come in here and kick out the bromine. Okay? So it is the Ff that's going to come in here and bond with the Li, the lithium. The correct formula for lithium fluoride is LiF. Li is a +1, fluoride ion is a -1. Don't put F2. Just because there's an F2 on the left side doesn't mean it's going to be F2 on the right. You got to create the correct formula for that compound. And then if it kicks out the Br, now Br is all by itself, and you're going to have to know, oh, Br, that's a halogen. Halogens are diatomic, so it's Br2. You can easily look up all the elements that are diatomic, and they're easy to memorize. So now we have the lithium bonded with the fluorine, and you've got two Brs bonded together to make this molecule over here. Let's balance this, because you can't have atoms disappearing or appearing. You have to account for them. So if I've got two Brs over on this side, where did those two Brs come from? Well, they must have come from the lithium bromide on the left side. That means I must add two of these molecules. Don't put a subscript here. Don't change the formula for lithium bromide. You're not allowed to do that. But you can double, triple, or whatever the number of molecules. So that means I must have had another lithium bromide molecule or compound here in my reaction. I got two of these. Bonds are broken here. All right. That means now I've got two lithiums. Well, I only have one on this side. That means there must be two of these compounds that are formed. I'm going to put a big 2 in front of those. And my two fluorines are accounted for because of the diatomic nature of fluorine over on this side. So I should have the same number of each element on both sides. I've got two lithium, yes. I got two bromine, two fluorine, two fluorine. Excellent. A student writes the following incorrect chemical equation for a double displacement or double replacement reaction between iron 3 and sodium hydroxide. Well, let's find out what's wrong here. First of all, it looks like the switch has been made. Iron is now going with hydroxide, as we see here. Sodium is going with the bromide ion, as we have here. But this is what the student did wrong. I'm just going to point it out. They figured, oh, since this is FeBr3 on this side, then it has to be Br3 on the other side. But that is not always the case, because it's combining with something different, a different metal. So you may not need Br3. You have to find the right ratio and the right formula for each compound when something new is created. Same thing here. Just because it's NaOH and only one OH in the compound doesn't mean it's going to be just one in this compound. So let's write the correct one as we've been talking about this. FeBr3. and NaOH. Those both are fine. Now bonds are going to be broken. New things are going to be formed. This Fe is going to bond with the hydroxide. Hydroxide forms a -1 ion. This is iron 3 because I see it takes 3 bromide ions. Each are -1 there, so this must be iron 3. I've got an iron 3 and a hydroxide coming together. So I'm going to need 3 hydroxides, like that. Sodium is going to bond with the bromide. Sodium is a +1 ion. Bromide is a -1. I just need 1 of each of those, not 3 bromides as is incorrectly written up here. So sodium, bromide. Those are the correct formulas. You have to write the correct formulas of your products. Now we balance it. Do I have an Fe on both sides? Yep, I got 1 of each. Do I have an A on both sides? Yep, 1 of each. Now we check Br. Br, I've got 1 here, I got 3 over here. Okay. Don't change the formula. Don't put subscripts. That changes the formula. You're not allowed to do that. You are allowed to double, triple, or quadruple, or whatever the number of compounds. So I need 3 Brs, so I'm going to have 3 different molecules of NaBr. Now I just tripled the NAs. I'm going to have to account for that over here by tripling the number of sodium hydroxide compounds. That is going to triple the number of OHs. Treat that as a whole group right there. And I already have that on this side. OH with a subscript means I've got 3 in that single compound. I've got the same number of every element, or groups of elements, in this case the OH, hydroxide, on both sides. Sometimes it's easier to work with a group, in this case the hydroxide, just work with that whole group instead of looking at the individual oxygen and hydrogen atoms to balance it. Okay? Check. Consider the following chemical reaction written as a word equation, and we are going to try to write the correct formulas and then identify what kind of chemical reaction this is. Hey, we got prefixes here. Diphosphorus pentoxide. Prefixes tell us how many. So diphosphorus, 2 phosphorus, pentoxide, O5, plus water, H2O, is going to create phosphoric acid. This is not hydro, so it's not binary. It is phosphoric acid. So we're going to have H, and the phosphoric goes with the phosphate polyatomic anion. Well, phosphate is a PO4. You may not know that, so you look it up. And the phosphate has a charge of -3. Again, you don't know that, so you look it up. So I need 3 hydrogens there because each hydrogen is a +1. This is a synthesis. How do I know? Has only 1 product. And write chemical formulas under the names. Yep, we did that already. And let's balance it. So if we've got, I'm going to leave water till last. Sometimes you do leave the oxygen or hydrogen or those compounds that have those 2 in there, leave them till last. I'm going to look at the phosphorus first. I've got 2 on this side. I'm going to need to double this compound right here because I did not retain the PO4. I don't have a PO4 on the left side, so I'm going to have to break apart the elements there. I have 2, so I put a 2 in front here. I got 2 phosphoruses. Now that's going to take care of, it's going to really change the other ones as well. I've got 6 hydrogens. 6 hydrogens. If I triple this, that's going to give me 6 hydrogens. But I'm running into a problem here because I've got, oh no, I'm going to be okay. I've got 2 times 4 oxygens. I've got 5 oxygens on this side and another 3. So I've got 8 oxygens on both sides. Hey, we balanced it. All set. Feels good when everything comes out right like that. Okay, chemists use their knowledge of synthesis, decomposition, single replacement, and double replacement to predict what will happen in chemical reactions. When predicting, meaning we're predicting the outcome, the products for a reaction, it is important to remember that atoms or ions will only combine in ways that make them stable, meaning they're going to be at a lower energy position. That's why they form compounds. Elements tend not to stay by themselves in nature. That's why if you do find them in isolation, they're probably fairly valuable. Those elements that can be stable in nature by themselves are valued. Gold, silver, those are highly valued elements. Okay. Otherwise, the reaction will not happen under normal conditions. They want to be more stable, lower energy position. This means that it is important to pay attention to ion charges, the natural state of elements, and the formulas of common molecular substances like carbon dioxide and water. It is only after predicting the products and writing the correct formulas that a chemist would then apply the law of conservation of mass and balance the chemical equation using coefficients as needed. So we balance this because you can't gain or lose things in a chemical reaction because mass has to be conserved. All right, and we do that. Remember, we balance these chemical equations with coefficients, not with subscripts. Don't change the formulas. Let's predict the products for the following. We're going to write the word equation if we have to. We're going to balance the chemical equation, and let's see how we do here. Now there may be possible answers, but we're just going to come up with some possible answers, and somebody may write something different, especially for decomposition and synthesis. Well, especially for decomposition, but the other two or the other three types are pretty set. Okay, so it's okay if you've got some variety. Okay, here we've got Al and N2, and it looks like you're starting with two different elements, and we're going to have a composition here, or called synthesis, I should say. So in this case, we've got Al and nitrogen are going to form a compound. You have to come up with the correct formula now. Just because it's N2 on this side, don't automatically put an N2 there. It might be, but it's no guarantee. Al as an ion is a 3 plus. N is a 3 negative. So I only need one of each. I don't need two nitrogens in that compound. It's just ALN. Now I need to balance it. Well, if I have two nitrogens on this side, because nitrogen is diatomic, I need two on this side. Don't put a 2 down here as a subscript, though. That changes the formula. You've got to use coefficients when you balance. I have two separate ALN compounds. Now I have two aluminum on this side, so I have to put a 2 in front of this aluminum, and that is your balanced equation for the synthesis equation of aluminum and nitrogen. Okay? All right, moving on, we've got dinitrogen monoxide. Dinitrogen monoxide, by the way, dinitrogen, two nitrogens, monoxide, and looks like it's going to break apart. So it's going to break apart into the elements. It's not just N and O. No. N is diatomic, oxygen is diatomic, so you have to write the correct formulas. Now I have to balance it. If I've got two N's on the right side, I have two N's on the left side, yes. But I got two oxygens on the right, I need two on the left, so I have to put a 2 in front of this formula, which now doubles the number of nitrogens on the left, so now I have 4, which means I have to put a 2 here as well. Balanced. Okay, and this one is a double replacement. I see where I have aqueous and aqueous solutions, and I have two ionic compounds, and they're going to switch partners. So as soon as I see two compounds like this, two ionic compounds, metal, nonmetal, in aqueous solutions, I know they're going to switch partners, or at least potentially that's what the reaction, that's what we're predicting. Okay? So I'm going to take the metal from the first one, Sr, and combine it with the non-metal part of the second one. And we're going to write the correct formula for this. I know Sr is a plus 2. Why? Because Cl is a negative 1 and it takes 2 of them in this formula. So Sr has got to be a plus 2. NO3 is a negative 1, so I need 2 of these. Plus, the silver is going to go with the Cl. Silver has a plus 1 charge. Chloride has a negative 1 charge, so I just need 1 of each of those. And you can put here AQ. Silver chloride actually is it's a compound that does not dissolve well in water. It is insoluble, so you might see an S there because when they come together, they're going to form a compound that no longer stays dissolved, and you're going to see actually a solid form, and it's going to settle to the bottom of your container when you mix these two solutions. And we've got now, just have to balance this, I think. Oh, they already put a 2 in front of there for us. That was nice of them. So I got 2 silvers, so I'm going to have 2 silvers here. That gives me 2 chlorine, which I have already here. And strontium, I've got strontium, and I've got my 2 nitrates, and we're all set. It is balanced. Chromium 3 nitrate. If you don't know nitrate, nitrate is NO3, has a negative 1 charge. Chromium 3, that means I'm going to need 3 nitrates. Zinc is a plus 2, chloride is a negative 1, so I need 2 chlorides. When this reaction occurs, the metals are going to switch places. These are 2 ionic compounds in aqueous solutions, and they're going to switch. Zinc is going to go with the nitrate. Zinc is plus 2, so I only need 2 nitrates this time. And the chromium is going to go with the chloride. It's chromium 3, so we'll assume it stays chromium 3. I'm going to need 3 chloride ions. Let's balance this. I got a zinc on both sides, that's set. I got a chromium on both sides. Looks like it's going to be the nitrate and the chloride ions that I have to balance. I'm going to have to put, notice right here, I've got 2 chlorides and 3. So I'm going to have to multiply one side by 3 and the other side by 2 in order to get 6 of each. 3 and 2. That doubles the chromium, so I'm going to put a 2 here, and that triples the zinc, so I'm going to put a 3 there, and that's going to take care of my nitrates as well, because 2 times that 3 gives me 6 nitrates, 3 times that 2 gives me 6 nitrates. Sodium and chlorine actually. Chlorine is a diatomic as well. So it looks like we're going to have a synthesis, 2 things coming together, kind of like up here in A, and it's going to form sodium chloride. That's the correct formula for sodium chloride. On the left side, chlorine, since it's diatomic, there are 2 of them, so I'm going to put a 2 here, and that doubles my sodium as well, and that's why there's a 2 there for us already. This is a single displacement or single replacement. The zinc's going to come in here and kick out the hydrogen, which acts like a metal, and you're going to form hydrogen, which is diatomic, so it's H2 always. That's the correct formula for hydrogen. And zinc chloride, that's the correct formula because zinc is a plus 2, chloride is a negative 1. So let's see. They already gave us a 2 right there. Why? Because I have to balance my hydrogens. That also allows me to balance my chloride ions, and the zinc is balanced, so check. Alright, our extension questions are going to talk about a 4th type of reaction. They are called combustion reactions, and these always occur between hydrocarbons. Hydrocarbons are molecules that have carbon and hydrogen in them. Those are the only 2 elements, carbon and hydrogen. Here's some examples: octane, butane, methane, often used for different types of fuels. Very combustible, they burn easily. These hydrocarbons, when they burn, they always are going to burn and consume oxygen as well. They need oxygen to burn. That's why oxygen is also a part of the reaction. They're going to get oxygen from our air and use that oxygen along with the energy that you put in And maybe you had a spark or you have a match or something like that. You have to put in energy, and now the reaction occurs. It's called a combustion reaction. You are always going to produce, always, 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 carbon dioxide and water. Those are always the products for the combustion of a hydrocarbon. Don't forget, oxygen is always going to be part of that reaction. Products here are always carbon dioxide and water. What reaction is common in all the combustion reactions in Model 2? Sorry, what reactant? The reactant is always oxygen. The fuel in most combustion reactions is called the hydrocarbon. I just told you that. Any molecule that has carbon and hydrogen only. Using the examples in Model 2, write a description for the classification of a substance known as hydrocarbon. Hydrocarbon has hydrogen and carbon in them, and when you write the formula, carbon is written first. Okay, so it's going to be a certain number of carbons and a certain number of hydrogens. They bond together to form different types of hydrocarbons. Predict the products of the following combustion reactions and balance each reaction equation. Always, always, always carbon dioxide and water. Carbon dioxide and water. How do I know that? Because I've got a hydrocarbon and oxygen, and they are being burned. Okay, the hydrocarbon's being burned, and it's using oxygen as part of the process. I just have to balance them though. Let's leave this oxygen until last. In fact, they gave us a hint here that I need 8 right there. So I need 5 carbons on both sides. Here's C5H12. I need 5 carbons, so I have to put a 5 in front of that. That gives me now my oxygens I'm going to leave till last. Let's come over here to hydrogens. I need 12 hydrogens. I have to put a 6 in front of this one. Let's see if the oxygens work out. I have 6 oxygens from this water molecule and another 10 here for 16. That's why they placed already for us an 8 in front of that, because 8 times 2 is 16. Let's balance this one. I have, oh, they already gave us a hint here. Let's 2 carbons. Okay, so we need 4 carbons. If we had gone ahead and done this without any assistance, we would realize that we needed 2 there eventually. But we're going to put a 4 there. Let's do the hydrogens. I have 4 here as well. Oh, sorry, no, just 2. My apologies. Okay, for a total of 4 hydrogens. How many oxygens does that give me? 4 times 2, that's 8, and another 2 here, total of 10. That's why it's multiplied by 5 right there. Alright, now we got some other compounds, and they can undergo combustion in a similar way. Predict the products of the following combustion reactions and balance each reaction equation. So in this case also we are going to create, these are different types of alcohols. This is isopropyl alcohol, and in this case this is glucose, a type of sugar, and the results are also going to be carbon dioxide and water. Actually it might be okay, so carbon dioxide and water in this case. So I'm going to go ahead and write the products, and then we just have to balance them. Again, leave oxygen till last, because we can write any number in front of this in order to balance the oxygens. I need 3 carbons, so I'm going to put a 3 there. I need 8 hydrogens. I'm going to put a 4 here. My oxygens then, I've got 4 oxygens from the water and another 6 here for 10. I'm going to put a 5 right there. And this one I need 6 carbons, so I'm going to put a 6. I need 12 hydrogens, so I'm going to put a 6 there, 6 times 2. And that gives me, oh, I realized that I made a mistake because I need 6, 10, I've got 10 and 11 oxygens up here. I just noticed that. So we're going to have to go back and fix that in just a second. Hold on. Let's see if this one works out okay. We've got 12 and another, we need 18, so if I put a 9, no, I have 18, I got 6 already here, so I just need 12 more. I'll put a 6 there to get my 12. Okay? Okay, so often if you find out that you get stuck, as we are here in A, what we can do, let's just double everything. Ignore this oxygen for a second. We're going to come back to that. It's going to be last. Well, let's just double everything. So 2, 6, 8. Now let's see what happens, because I'm going to need an even number of oxygens for this to work. So that's why I doubled this to get 2 oxygens in here. So now let's check our oxygens. We've got 2, sorry, let's do the right side. I've got 12 and another 8, so that gives me 20. So I have 2 right here as in this reactant, so I'm going to need another 18 over here, so I'm going to multiply that by 9. Okay, so it's a bit of a trial and error process. If it doesn't work the first time, maybe you have to change the numbers, or you double everything and then fix that. But remember, keep oxygen, or if there's a lone element like hydrogen or something like that, keep that till last, because those can easily be manipulated. For each of the reaction types in Model 1, explain why a combustion reaction cannot be classified as that type. Use a complete sentence in each answer. So basically what they're saying is, if you look back up in Model 1, you want to make sure that you can differentiate between anything in Model 1, synthesis, decomposition, single replacement, double replacement, and combustion. So 1, you have to make sure that, you just have to make sure that the criteria for the combustion is being met. So is it combining with oxygen, and are you creating carbon dioxide and water? That is the main criteria for it to be a hydrocarbon combustion reaction. Okay, so that might help. All right, great job, and we will be working a lot more with balancing equations, because it's not going away. We need to continue to balance equations as we look at these reactions, as we look at what's going to be called stoichiometry, which is basically working with moles, mole ratios, determining the mass of something that is produced or needed in the reaction. So lots of fun things ahead of us. All right, great job, and we'll see you in the next one.